is the process in which there is least degradation of energy, because all the heat supplied to the system is converted into work. Coming to the next process, that is adiabatic process. Adiabatic means there is no heat transfer between system and surroundings, that is Q is equal to 0. The reversible or frictionless adiabatic process is also known as Entropic process, because in this process the entropy of system remains constant. Iso means same. Isoentropic means constant entropy or same entropy. The adiabatic process can be called as isoentropic only if it is reversible. The equation of process is PV to the power of gamma is equal to constant, where gamma is the adiabatic index of gas. Considering a closed system or the gas entrapped in a piston cylinder arrangement, where the system is perfectly insulated from the surroundings. This is insulation, where heat can neither enter the system or rejected from the system. Heat cannot be rejected, or heat cannot be supplied to the system. Still, the system could do work on the surroundings at the cost of decrease in its internal energy. The process on PV plane can be represented as a curve, which is a steeper curve than isothermal curve. The equation is P1 V1 to the power of gamma is equal to P2 V2 to the power of gamma. That can be written as P1 by P2 is equal to V2 by V1 to the power of gamma. Combining this isoentropic relation with the ideal gas equation, that is P1 V1 by T1 is equal to P2 V2 by T2. This is ideal gas relation. Assuming that the working fluid is ideal gas, we get two other important isoentropic relations, namely P2 by P1 whole to the power of gamma minus 1 by gamma is equal to T2 by T1, where T2 and T1 in Kelvin only. Also V2 by V1 whole to the power of gamma minus 1 is equal to T1 by T2. These two relations are known as strictly isoentropic relations, which cannot be written for irreversible adiabatic process. They should be written only for the reversible adiabatic process, also known as isoentropic process. The work done in a isoentropic process undergone by an ideal gas in a reversible adiabatic process undergone by closed system can be given as integral PDV, which can be integrated and obtained as P1 V1 minus P2 V2 by gamma minus 1 kilojoules per kg, which can also be written as RT1 minus RT2 by gamma minus 1, that is R by gamma minus 1 into T1 minus T2 kilojoule per kg. But R by gamma minus 1 is termed as CV. Therefore, work done in a reversible adiabatic process can be written as CV into T1 minus T2 kilojoule per kg. But for any process undergone by ideal gas, CV delta T is nothing but delta U. Therefore, work done in reversible adiabatic process is nothing but delta U kilojoule per kg, where U is the internal energy of the gas. Applying first law of thermodynamics to the adiabatic process, Q minus W is equal to delta U, but Q is 0 in the adiabatic process. It means W is equal to minus delta U. Hence, work done by any adiabatic system can be taken as minus delta U, which is equal to decrease in internal energy of the system. This equation holds whether the adiabatic process is reversible or irreversible. The slope of reversible adiabatic or isoentropic process on PV plane is dP by dV, the slope of adiabatic process on PV plane, or reversible adiabatic process or isoentropic process on PV plane is given by minus gamma P by V. That implies the slope of isoentropic process on PV plane is equal to gamma times the slope of isothermal curve on PV plane, both intersecting at a point, which can be shown on PV plane as, if this is isothermal, this is adiabatic. This is PV is equal to constant. This is PV to the power of gamma is equal to constant. 1 to 2 is isothermal. Say 1 to 2 dash is a reversible adiabatic or isoentropic. Isoentropic curve is steeper than isoentropic curve isothermal curve, intersecting at point 1. Now let us indicate all the 5 thermodynamic processes on a single tabular form showing the heat interaction and work interaction and PV diagram. First process is isothermal. Q, W, delta U, PV plane. Q is equal to the work done. Here P1 V1 log V2 by V1, that is the work transfer. Change in internal energy is 0. On PV plane it is shown as a curve having a lesser slope of minus P by V. Next, coming to the adiabatic process, which is also reversible, Q is 0. Work done is P1 V1 minus P2 V2 by gamma minus 1. Change in internal energy is equal to W. The curve is a steeper curve having much more slope than that of the isothermal curve. Slope is minus gamma P by V for isoentropic process. Next, isochoric process. Q is mCV delta T. Work done is 0. Change in internal energy is equal to Q. The process is represented as a vertical line. Then isobaric process. Q is mCP delta T. Work done is P into delta V, or P is equal to P into V2 minus V1. Delta U is mCV delta T. The process is indicated as a horizontal line on PV plane. Coming to the fifth process, that is polytropic process. The equation of process is given as PV to the power of n is equal to constant, where n is equal to polytropic index. If we substitute n is equal to 0, implies we will obtain isobaric process. If n is equal to 1, we will obtain PV is equal to constant, which is the equation for isothermal process. If we substitute n is equal to gamma, implies we get PV to the power of gamma is equal to constant, which is the equation for isoentropic process. If we substitute n is equal to infinite, we get volume is equal to constant, which is nothing but isochoric process. If we substitute n greater than 1 but less than gamma, we will obtain PV to the power of n is equal to constant. It can be called as polytropic. For example, PV to the power of 1.25 is equal to constant, where if gamma is equal to 1.4, where n is equal to less than gamma, because n value is chosen here as 1.25, which is less than gamma, where gamma is 1.4, the process is termed as polytropic process. In the polytropic process, n value will be greater than 1 but less than gamma. The work done in a polytropic process is calculated as P1 V1 minus P2 V2 by n minus 1. The heat transfer in a polytropic process is given as gamma minus n by gamma minus 1 into work done. If we substitute n is equal to gamma, which is adiabatic process, Q becomes 0. Now coming to the first law of thermodynamics, applied to a open system which is undergoing a steady flow process, the assumptions are steady state process, process may be reversible or irreversible. Considering the open system, which is also known as control volume, bound by control surface. Section 1 is the point where mass is entering, and section 2 is the one where mass is leaving. There is heat supply to the control volume. There is shaft work done by the control volume, W shaft, which is treated as positive because it is done by the system. Q supply is also positive according to the sign convention given to the heat. Let m dot 1 is equal to mass flow rate of fluid entering control volume in kg per second. M dot 2 is equal to mass flow rate of fluid leaving control volume. The mass that is entering into control volume shall bring in 4 forms of energies. They are: number 1, internal energy U1, flow energy or flow work P1 V1, kinetic energy, that is V1 square by 2, potential energy, that is G into Z1. All the energies are in joule per kg. Similarly, the mass that is leaving control volume takes out 4 forms of energies, namely internal energy U2, flow energy or flow work P2 V2, where V is the specific volume. Number 3, kinetic energy, that is V2 square by 2, where capital V is the velocity of the fluid at exit. Potential energy G into Z2. Here Z1 and Z2 are elevations of sections 1 and 2 respectively above some arbitrary datum. All the energies are mentioned in joule per kg. Steady flow of fluid means the properties of fluid like density, pressure, etc. at a given location in the control volume should not change with respect to time. This is the meaning of steady flow of the fluid. Applying continuity equation or conservation of mass principle to the control volume. For steady flow, rho 1 A1 V1 should be equal to rho 2 A2 V2, where rho 1 and rho 2 are densities of fluid at sections 1 and 2, or otherwise the continuity equation can be written as A1 V1 by small v1, where small v1 is the specific volume at section 1, is equal to A2 V2 by V2. V1 and V2 are the velocities of the fluid at sections 1 and 2. Mass flow rate being given in kg per second. That is, m dot 1 should be equal to the m dot 2. Writing energy balance equation for the control volume for steady flow, the rate of energy entering control volume in joules per second should be equal to rate of energy leaving control volume in joules per second. The energies that are entering the control volume, if we write, the mass that is going along with the control volume will take in internal energy, flow energy, kinetic energy, and potential energy. Plus there is heat supplied into the control volume. That should be equal to the m dot 2 into U2, that is internal energy leaving the control volume, plus P2 V2 flow energy leaving the control volume, plus kinetic energy leaving the control volume, plus potential energy leaving the control volume. Plus there is shaft work done by the system. In this equation, Q is positive, W is also positive. Now let us assume that m dot 1 is equal to m dot 2 is equal to 1 kg per second. Then heat supplied per unit mass is Q divided by m, that is small q, joule per kg. Similarly, work done by unit mass leaving control volume small w joule per kg. Small w indicates the shaft work done by the unit mass of the fluid, the work being done by the system, which is a positive. Substituting these values in the above equation or energy balance equation, we can say we get U1 plus P1 V1 plus V1 square by 2 plus G into Z1 plus small w, which is the work done by unit mass of the fluid passing through the control volume, that should be equal to U2 plus P2 V2 plus V2 square by 2 plus G into Z2. Here the capital V's are indicating velocity, small v is indicating specific volume in meter cube per kg. Replacing U1 plus P1 V1 as H1, that is enthalpy entering the control volume in joule per kg, and U2 plus P2 V2 is equal to small h2 enthalpy leaving the control volume at section 2 in joule per kg. We get H1 plus V1 square by 2 plus G Z1 plus WSH, SH means shaft work, is equal to H2 plus V2 square by 2 plus GZ2